Well, there you go. All right, but of course I'm not starting just yet. Start at 10:10. There we go. Just getting some things finished up. There we go. And there we go. All right, I'll be back. And we're back. In the description to this video, there's a link to a PDF file of the problems that you guys just did in this practice quizzes. And in the link, there are answers, an answer key at the bottom of that page. But I wanted to take the time to explain these problems. Again, it just being a practice, this did not count against you. But ultimately, I would like to fit in another assessment in regards to these problems, just so we're all on the same page. Kyle, you can't time people out unless they participate in the chat. You know that. Oh, hey, Joe. No, you didn't miss stuff, Joe. We literally just got started. I don't get started till 10 minutes into the stream anyway, just so people can kind of get in and get settled and open up whatever files they need to open and whatnot. And here we are. Well, yeah. Anyway. I'm just reading Joe's thing. I just want to make sure I didn't miss the stream. I got you, Joe. I got you. Anyway, yeah, we can all chat at the end. But what I wanted to do first and foremost, I wanted to go through these problems. I wanted to make sure I answered questions if you guys had them and was able to explain whatever we needed to explain. So, number one. Number one is asking for you to identify the confidence interval used in the figure below if the shaded area is equal to 0.05. Now, when I originally went over confidence intervals, I talked about the general idea of a confidence interval is attempting to capture the true mean, attempting to capture the true mean. And there is a certain percentage confidence that you have that your interval has captured the true mean. So let's just pretend, this is an example of an interval from the dot to the dot, line to the line. That would be the interval, but how confident am I? Depending on the percentage confident that you are, which in this case, it's 90%, the idea being that you're hoping that you're capturing the middle 90%. You're hoping that you capture the middle 90%, but there is no guarantee. But if you did capture the middle 90%, that means that you did not capture the outside 10%. 5% here, 5% here. That's what this thing was referring to. Number two, the confidence level of an interval. Let me remove these papers from underneath. There we go. Much better. So I'm not. There we go. Good. Number two, the confidence level of an interval estimate of a parameter is the probability that the interval estimate will contain the parameter. Why is this thing so dark? Whatever. With number two, just first and foremost, it's true. But let's just decipher that a little bit as to why. Yeah. The confidence level, which before, let's just say was like 90%, is the probability that an interval estimate will contain the parameter. Now, if we were in AP statistics, technically, I would dance around this and actually say that that's not precisely what the confidence level means. But let's just put it this way. Let's just say that here's an interval, 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 here's an interval. Just a bunch of random intervals that were created based on whatever samples were taken. And what I have in black here, let's just say that that represents what the true mean actually is. Hopefully you can see that some of those intervals, actually 4 of them, contained that true mean, and 3 of them did not. These intervals, whatever they are, from what number to whatever number you want. The general idea, let's say, behind a 90% confidence interval is that 90% of all created confidence intervals would capture the true mean and 10% would not. In that sense, yes, you could say it's the probability of the interval estimate containing the parameter being the true mean. Remember, parameter goes with the population parameter, The whole interval estimate of a parameter thing, that's just like fancy stat talk. But in general, yes, the confidence level is the probability that your interval estimate will contain the parameter. It's a weird kind of way of putting it, but yeah. In general, you could say that you are 90% confident that your interval has captured the true mean. We wouldn't typically say there's a 90% chance that our intervals contains the true mean. We wouldn't typically say that in a p-stat, but for our purposes in Algebra 2, that would be okay for now. Let's go to number 3. Find the z value. Oh, I can't see it. Find the z sub c for the 90% confidence interval. Now, this was something that in the video that I made for you guys, we were able to just basically list them out. In fact, let me get the actual paper so we're all on the same page in regards to this. I always keep everything that I write. So let's see here. That was z-scores. There we go. So in the notes that I gave for you guys, you could hopefully see that right there. The z value for the confidence interval, 90%, 95%, 99%. Of course, confidence intervals don't have to remain those 3 percentages. You can make a confidence interval whatever percentage you want. It's just that these are the most typical percent confidence levels that we use. So in this case, for this problem, the answer has got to be B, and it is. Of course it is. The positive negative doesn't really necessarily matter because in this case, for 90%, and I know I drew this earlier, but I'm going to draw it again. I'll move that down a little bit. There we go. Let's just say it was 90% right here. Then the z-scores would technically be 1.645, negative 1.645, trying to capture the middle 90%. Again, the definition of z-score given in that previous video that we covered. Number 4. A research company wants to estimate the proportion of people who like oatmeal. They want the confidence level to be 95%. The company gets 325 people to sign up for the survey, but on the day of the survey is issued, only 250 people show up and take the survey. What happens to the confidence interval? Now, the formula that I gave you guys was something along the lines of this. This was the formula that I gave you guys. Now, this problem, I think most people got wrong on this one just because they didn't really know how to handle it. It wasn't something that I had discussed, but obviously now I'm discussing it. In this instance, x bar would be the middle of the interval, and the interval would be would have an upper limit where you add this amount and a lower limit where you subtract this amount, and I labeled this the margin of error. The margin of error, it's the plus or minus. It's a similar plus or minus that you have in the quad formula, where you'd have to add an amount and subtract an amount to get 2 different answers. In this instance, when you add and subtract the amount, you get the lower and upper limit of the interval. Now, the only thing that changed in this particular problem was the number of people who showed up to take the survey. In this case, that affects the denominator. For this particular problem, I'm sorry, Kyle, you happen to be wrong. The more people, the more people that show up, the smaller the margin of error. Because the square root of n is in the denominator, the larger the value of n, as n gets larger, margin of error gets smaller, and vice versa. If your sample size grows smaller, that actually increases the confidence interval, extends it. Oh, yes, of course, you did say it. You did not say it. Stop it, Kyle. But that's what ends up happening. As n gets larger, the margin of error gets smaller. As n gets smaller, the margin of error gets larger. The general idea being that the more people that you have, on the quizzes, the more people that you have in a sample, the more people, the less variability that will actually take place. The less number of people, the more variability that would take place. Think of it in the sense of like flipping a coin. If you flip a coin 10 times, you could easily have like 7 tails. Sure, 7 out of 10. But if you flip that coin 100 times, it is not likely that you would get 70 out of 100 tails. What's more likely is the more flips that you take, the more flips of the coin that take place, the more likely that your sample will get closer and closer to that 50-50 proportion. It's the general idea of the law of large numbers. Not the law of averages, but the law of large numbers. The coin remains a 50-50 coin every single time. But the more flips that you take, the less variability that will take place. And it's because that sample size is on the bottom of a fraction. It would actually decrease that margin of error. Number 5. Sample size of 64 is drawn from population of standard deviation is 5.6. Find the margin of error for 99% confidence interval. Well, if I'm going to find the margin of error for that, I am going to need that z value for 99%, which, according to my notes, the z value for 99% is 2.576. And the formula for the margin of error would be that plus or minus z times s over the square root of n. That's what you would have to calculate for this particular problem. So, if I was going about that here, 2.576 times 5.6 divided by the square root of 64, 1.8032, which clearly has to be c. But that's the calculation that would have to take place. You'd have to do 2.576 times 5.6 over the square root of 64. That calculation will get you that margin of error. Number 6. A large sample has a mean of 7.1 and an s over square root of n equals 2.3. So automatically, they're telling you that this calculation is already 2.3. They're not giving you the sample standard deviation. They're not giving you the sample size. They're just giving you that full thing, the full calculation of x bar plus or minus z times s over the square root of n. So sample mean is 7.1. They want a 90% confidence level. 90% confidence would put us at 1.645 for the z. Again, that list was given to you in the notes. I should probably put it on a post-it, just in case we have to deal with it for later problems. So let's see, 90% was 1.645. We also had a 95%. Where is it? The 95% was 1.96, and 2.576 for the 99%. So I'm going to leave this aside for the time being, just as a reference, and I'll bring this back in, because this was part of our notes. Put that up there. So with this calculation, let's see. I would have to do 7.1 plus 1.645 times 2.3. That would give me my upper limit, and I would have to do it again to get the lower limit. Number 6, the answer has got to be A because of that calculation. Nice. Number 7. Move this over. There we go. Let's see, number 7. Oh, words. When you guys see words, you tend to panic. That's okay. An IQ test was given to a simple random sample of 75 at a certain college. The sample mean was 105.2. Scores on the test are known to have a standard deviation of 10. It is desired to have a 90% confidence interval. They want the critical value. Yes, Kyle, words. This is all they want. Find the critical value, which 90% confidence puts us at 1.645. Now, this problem was a little bit mean, I guess, in the sense that they gave you these two answers, C and D. Technically, the plus or minus is already in the formula. The formula being x bar plus or minus z times s over the square root of n. Because of that, the critical value, the z value, was just this number. Got to be C. Little bit of a trick, but again, this was just a practice. Number 8. If the 95% confidence interval for a population mean is that's the confidence interval, then it is likely that the true population mean is greater than 130. No. Now, right off the bat, clearly the answer is not D, so don't worry about that. But again, think of what it means to be a 95% confidence interval. If I say I'm 95% confident in this population mean, or this interval for the mean, I'm saying I am 95% confident the true mean is in the interval 114.56 to 125.54. I'm 95% confident that that interval contains the true mean. Now, could I be wrong? Yes, I could be wrong. But I'm saying I'm 95% confident. Or I'm saying that if there were, thousands and thousands of intervals being created, 95% of them would capture the true mean and 5% would not. I'm simply hoping that I'm one of the 95%, which is likely. So, is it likely that the true mean is greater than 130? No. No, absolutely not. I mean, it could be. That's why they're leaving a little bit of wiggle room with the chance. They're saying, is it likely that it's greater than 130? No, it's not likely. The reason? Because that number is not in my interval. Number 9, true or false? The more confident you want to be, the smaller your confidence interval will be. Okay? The more confident you want to be. Now, when I'm talking about confidence, I'm talking about percentages. 95%, I'm sorry, 90%, 95%, 99%. And in this case, those percentages affect my z value. Those percentages affect my z value. Now, if you notice, the more confident that you are, the larger the z value. The more confident that you are, the larger the z value. Well, what does the z value affect? The z value affects the size of the margin of error. In fact, the more confident that you are, the larger your margin of error, the larger your confidence interval. Oh, what am I doing? Yeah, the answer is definitely false. Sorry, I got distracted by Kyle's messages. Kyle, you say true a second. Right. On the quizzes again. Yeah, but the answer is definitely false. But the words that I used are the rationale behind that. The larger the confidence, or the more confidence that you have, the larger the z. The larger the z, the larger the margin of error. The margin of error decides how big or small the confidence interval is going to be. Number 10. Let's see what we got here. There we go. True or false? The larger the confidence interval, or the larger your confidence interval is, the more sure you can be. The larger the confidence interval, the more sure you can be. Yeah, that one is definitely true. The rationale, again, the larger the confidence interval, your interval is getting larger. So this interval versus this interval. In this case, yeah, the higher the confidence. This could be like a 90% confidence interval, and this could be a 99% confidence interval. That's how those things could potentially take shape. The larger your confidence interval, the more sure, the higher the confidence level you can be. Yeah, for the most part. I mean, obviously, there are other ways to increase the size of your confidence interval. You could decrease the sample size if you wanted to. That's the one thing you can control. Of course, you can control the percent confidence that you are. That's a bit more easier to do. Obviously, if you get like 200 samples, you can't just decrease the number of samples. You have 200. You can't control that, but you can control the percent confident that you are. Number 11. In a research report, the term significant is used when the null hypothesis is rejected. Now, this is really weird. This is the null hypothesis, whatever that null ends up being. And the general idea is that we would reject that null hypothesis. We would reject that null hypothesis if, so hold on, reject if p-value is less than your alpha level, which in most cases your alpha level is 0.05 unless they say otherwise. You would reject if the p-value is less than the alpha level. You would say, and here's the phrase, that you have statistically significant evidence against the null hypothesis. So the answer is true. If you have statistically significant evidence against the null hypothesis, then yes, you would reject that null in favor of whatever the other claim happens to be. It's, again, think of someone being put on trial for murder or something along those lines. If you have significant evidence against the person who was on trial, then you have obviously very good evidence that their innocence should be rejected. The null hypothesis is basically their innocence being put on trial. And ultimately, you either reject their innocence or you fail to reject their innocence. Number 12. In a research report, the results of a hypothesis test include the phrase, quote, z equals 3.15 and p-value is less than 0.01. This means that the test failed to reject the null hypothesis. Well, no. Look at the statement that I have above. You would reject if the p-value is less than your alpha level. Your p-value is less than 0.01, which I don't know what that would be. I don't know what number that is. But it means that you would reject. This type of p-value indicates a rejection, which means that 12 has to be false. Number 13. The weight of the average 6th grade boy is 89 pounds. The principal of the school feeds them steak for first semester to see if their weight changes. That's a weird school. What are the null and alternate hypotheses? Well, the assumption is that, okay, the principal is trying to see if their weight changes. The principal's trying to see if their weight changes. Which means, in his mind, since he's saying that phrase, it wouldn't matter if their weights went up or if their weights went down. Clearly, they would most likely go up. I don't know. I don't really care. But they would change, which means either positive or negative. The null hypothesis is no change. The null hypothesis is there's nothing going on. No change. Whereas the weight changes greater than, less than, there's a not equal to. Number 13 should be D, and it is. Your null and alternate hypotheses should never be exactly the same thing. They should never be exactly the same thing. It's an alternate hypothesis. By definition, it has to be different. So please keep that in mind. Obviously, the assumption is, well, maybe they'll gain weight. But for B, in this case, because he's saying they want to see if their weight changes, it's got to be not equal to. Number 14. A car manufacturer advertises that its new subcompact model gets 47 miles per gallon. If mu, now mu is the population mean, if mu is the mileage of these cars, what could be the null and alternate hypotheses if we wanted to check to see if the car's miles per gallon is overrated? Is the car's miles per gallon overrated? Now, that's a claim. If the car's miles per gallon is overrated, then perhaps the miles per gallon is too high if it's overrated. Meaning, we're trying to see if the car's gas mileage is actually less than what what they advertise, let's say. You're looking at the wrong one. I gotcha. Now, the null hypothesis would be nothing has changed. Nothing has changed. Innocent until proven guilty. That applies to all of them. Now, obviously, this one is nullified for the alternative, because the alternate has to be different than the original. But if they're wanting to check to see if the car's miles per gallon is overrated, meaning, I don't think it's that high, the answer's got to be B. The alternate being, I think it's less than 47. That's my claim. Yeah, less than 47. Number 15. I've been saying this for like 3 problems now, I think, or something along those lines. The null and alternate hypothesis cannot be the same. They cannot be the same. By definition, alternate hypothesis has to be different than what the original one was. Pretty straightforward, my opinion. But anyway. Number 16. Here we go. A company's old antacid formula provided relief for 70% of the people who used it. Okay. That's the old formula. The company tests a new formula to see if it is better and gets a p-value of 0.27. Now, all right, we could write out a whole bunch of stuff for this. Now, obviously, I know what the question's asking, but let's just write out a few things for what this thing is really saying. They're saying, oh, we're testing out this new formula, and we want to see if it's better than the old 70%. If it's better than the old 70%, then we're trying to claim that the new one is greater than 70% relief. They tested that, and they got a p-value of 0.27, which is less than the alpha level of typically 0.05. We would fail to reject. Or we would say there's not enough evidence to suggest that the new formula is better than the old formula. Now, that's not what the question's asking. The question just wants to know, what would the null hypothesis be? Now, I put 0.70. I did that just out of habit, because typically when I write 70% in my mind, I automatically clip it to be a decimal. But in this answer, they didn't do that. They wanted to keep it 70%. Weird people. But that's the thing, yeah. Again, 0.27 would be the null hypothesis. I don't know where they got the 0.189 or the 18.9. Maybe they actually multiplied them. Hold on. Maybe they did 70 times 0.27. Yeah, they did 70 times 0.27. Or 0.70 times 0.27. Yep. That's where they got those. I don't know where they got those. That has no basis in reality. Number 17. Accompanies old antacid formula. It's a similar problem. They test a new formula, see better, 0.27. Now they changed the alpha level. Oh, you can't see it. Can't see it. There we go. They changed the alpha level. We typically use 0.05, but now they're saying, hey, we're using 0.01, but it remains the same. If the p-value is less than alpha, you reject. Otherwise, you fail to reject, which in this case, there's your p-value, there's your alpha level, you would fail to reject. Is it reasonable to conclude that the new formula and the old one are equally effective? No. With a high p-value, we would fail to reject the null hypothesis. Yeah. That is a proper conclusion. We would not reject it. With a high p-value, it shows the NS is working. Absolutely not. Yes, with a with the high of a p-value, it shows more likely that no. We would fail to reject the null hypothesis. Now, like I said, in the description to this video, is a link to the PDF that you can view that has all of these problems on there, and the last page on that PDF has the answer key, the same answer key that I just went through. I have not decided exactly when I'm going to assign the assessment for this. I may assign it either Thursday or Friday. But that would be we'd be looking towards the last key assessment of this particular marking period. So please be on the lookout for that. That concludes this particular lesson. And I will put that in the timestamps when, I'll put that into the timestamps when this video is finished processing. What's up, Joe? Well, yeah, I only had that many problems to go through. It's been 45 minutes. Yeah, exactly. This is not fair. I didn't sign off yet. Oh goodness. I want to waste an hour. If you want to hang on for an hour, I'll hang out for a little bit longer. I mean, I can't promise, but I can hang out for a little bit longer. I don't know. What are you guys doing? Oh, goodness. Yeah, the year's very much wrapping up at this point, you know. It's crazy to think about that, how quickly it's just wrapping up, because according to our schedule, next week should be senior finals, which I think they just kind of like tried to envelop all finals into that for some reason. I don't know. But we were told by our supervisors and whatnot that, yeah, you should be wrapping things up, make sure you have the appropriate number of assessments, and obviously final exams are not voluntary, optional. That's kind of where we're at. It's really strange. Here, I'm gonna put a link to a video that you guys can watch. Get shareable link and paste. Check out this video. Boom. That's me getting one of the top times in the world for a game on the old NES. Some of you may have already watched it. But here, I'll post the leaderboard. Come on, leaderboard. Do your thing. Wrecking Crew. There we go. Copy and paste. Check out this leaderboard. 13th on the leaderboard. Woo! I mean, I have to practice that game. I really do. But with practice, I have a very, very outside chance of cracking, let's say, the top 10. Maybe even better. Who in the world knows? You're talking about like seconds at this point. Yeah. I mean, it's a pretty fun game. I had that game. I had that game when I was a kid, and I actually texted my sister about it. And I'm like, I'm like, hey, you remember this game? And she's like, yeah, yeah, I remember that game. Joe, do I really want to hear this joke, or is it pretty bad? Joe, I'm gonna give you a chance here. I'm probably only gonna be here for a few more minutes, let's say, maybe like to 50 minutes or something like that. But I'm gonna give you a chance with this joke. Do me proud, Joe. Do me proud. What are you gonna do with this joke? Better be good. I have my hand on the mouse. I just heard the setup, and I'm already dreading what the answer would be. Kyle, we shouldn't be scared. I'm waiting for it, Joe. I think we're all waiting with bated breath. Was that the joke? Joe, I usually get your jokes. Am I supposed to be getting this one? Sorry, I'm laughing at Kyle's response. I'm just saying, it would be if. How is it not hard? I'm gonna need a little more explanation. No, because they're at the beach, then like a ton of people would be wearing like sunglasses. What if they're sitting down in a beach chair? There are some people who are blind, and it's difficult to tell if they are blind. I don't get it. You think you get it? Wait, it's inappropriate if you're right? I don't get it. I'm not even gonna pretend that I get it. Joe, where are you getting these jokes from? waiting. I'm sorry, just repeating himself and getting louder. On that note, click the notification bell, subscribe, do all those things. I'm gonna sign off.